Hello everyone. Hello David.
Sorry, let me unmute myself and put my camera on. Hello, everybody. How is everybody today? Good. Right. Well, we've got a small group, so entirely up to you. I'm not going to force anybody to put their cameras on, but do feel free to turn your cameras on if you would like to. Do also feel free to just shout out, as well as putting answers into the chat. We've got today as a topic which I've got a real love-hate relationship with it. Fundamentally, it's one of my favorite pieces of mathematics. So I really think you are in for a absolute treat. The reason I've got a slightly hate relationship for it is it's one of these things which, in my day job as a maths teacher, it can be one of the most frustrating topics to teach because it's something which is so much on the fringe of GCSE that for a lot of students, it's just a tiny little thing which they need to memorize and which is not sort of sufficiently rich that they get any insight into why it's such a nice topic. So we're going to be looking at constructions and loci, and I'm just going to share my screen. And I just need to get the right sheet. I've accidentally put in the coordinate geometry sheet. And actually, before moving to the sheet, I'm going to start with something which is a bit different to the sheet, just in case you've already seen it, and hopefully something which is unfamiliar to you. I'm going to consider the following problem, okay? I'm going to tell you that points A and B are given. And I'm going to tell you a fact about point P, okay? And this is introducing the main idea of the sheet. So the point P is such that angle APB is 90 degrees. And A and B are fixed. Okay, first of all, is the point P uniquely defined by that definition? So is there a single point P that satisfies that geometrical condition? No, there's lots of points, okay? And I don't know how much people have looked at the sheet or how much people are aware of, but I'm going to convince you that there's lots and lots and lots of sheets of points. So I'm going to imagine that I walk in some straight line from A. A little piece of geometry, which we for sure will see later on this evening, is that at some point on this blue line that I've just drawn, I can find the shortest, I can find the point which is the closest point from B to that line, such that I'll call that point Q, such that OQB is a right angle. So imagine you're standing in the middle of the road, busy motorway, and you want to get to the pavement as quickly as possible. You would just run out of, or walk safely out of the road in the direction that's perpendicular to the pavement. So I can always draw this line from B, which is perpendicular to the line, and I've got a point Q, which is a right angle. So it's certainly not a unique point. In fact, what I've just shown is that that there is a point satisfying this condition on any line that I draw from A. So if I drew this line from A, I could also drop a perpendicular. And there'd be another point. I'll call that R, where that is a right angle. So there's lots. So the point P is not uniquely defined, but it's also not completely arbitrary. Okay, there's plenty of points which is not a right angle. In fact, you can convince yourself that on any one of these lines that there is a unique point. So what there must be is there must be some set of points P that satisfy this condition, and a large number of points P that don't satisfy this condition. The name for such a condition, so the name for a curve or a set of points that is specified by a geometric property, this is called a locus. Okay, not a locust, that's a type of insect, but a locus. Does anybody want to suggest what the locus of the points satisfying P are? So if I was going to join together all the points that satisfy this condition, presumably it's some sort of curve. Does anyone want to suggest what type of curve it is? Okay. So a couple of people have suggested that it's a circle with diameter AB. And I hope at least one of those people, so firstly, congratulations to those people. They are correct. I hope that at least one of those people is going to be brave enough to unmute themselves, or failing that, type it into the chat and explain why they said it was a circle with diameter AB. And then we can listen, the rest of us can listen carefully and try and decide whether their argument is full, whether it's complete, what it shows. So, Nagv, you were first. Do you want to try and justify to me that it's a circle with diameter AB?
I mean, we learned this as a circle theory in school, but I'm guessing it's something to do with a cyclic quadrilateral and the fact that opposite angles in a cyclic quadrilateral sum to 180.
So if I've got a circle, you're telling me that if I draw any quadrilateral, the opposite angles add to 180.
Yeah.
Why does that help me here?
Sorry?
Why does that prove? It's not at first glance, that's not obvious that helps me show that the set of points P such that APB is 90 degrees is a circle. What was the other circle theorem you mentioned?
The one that angles in a semicircle sum to an angle in a semicircle that is drawn from the diameter is 90 degrees.
Right, excellent. Okay, so what Nag has said is that he learned at school that if we draw a semicircle, then if we take any point on that semicircle, then this angle is 90 degrees. For the sake of completeness, because we are mathematicians, I will prove that fact. If I draw the radius here, then I've got two equilateral I've got two isosceles triangles. I can say that if I label this angle in here as x, this angle in here is also x. So this angle, the third angle in that isosceles triangle, APO, sums to 180, so it must be 180 minus 2x. The other part of that angle that lies on AB must be 2x. And now if we consider the second isosceles triangle OPB, these remaining two angles must be equal. So they must each equal 180 minus 2x divided by 2, which is 90 minus x. And now if we consider the angle APB, that angle is x plus 90 minus x, so is 90 degrees. Okay. So what Nag has said is Nag has quoted this circle's theorem. So Nag V has said that if P lies on a semicircle with diameter AB, sorry, on a completely garbling what I'm trying to write, lies on a semicircle with diameter AB, then angle APB is equal to 90 degrees. Is that enough? And this is a really important question of logic. Is this enough to show that the set of points P that are such that APB equals 90 degrees is a circle? Who thinks that Nagvi's argument is sufficient? Who thinks that it's missing something? So Nagvi has shown that if we lie on a semicircle, then the angle APB is 90 degrees. So someone said that so Marcus said that it's sufficient. Okay. On its own, I'm going to try and convince you that it's not sufficient. Right, so Luke M has said, my gut feeling is that it's a decent chunk of the argument, but it's not the whole argument. So let's really drill into what Nagvi has shown us. So what Nag has done is he's quoted this circle theorem, which says that any point on a semicircle subtends an angle of 90 degrees. And obviously we can take the semicircle beneath and that would give me the whole circle. So what Nagvi has shown me is that if I lie on the circle, let's try and do it and let's get an ink to shape. So here's my circle. What he's shown me is that if I take the points A, B, and let them be the diameter of a circle, then any point P will, on the circle, will satisfy the conditions of the locus. But what the argument does not yet show is that what there could be is there could be points that are not on the circle that also satisfy the locus. So Nagvi's argument on its own doesn't show that there might be some point here Q outside of the circle, but which nevertheless is such that the angle AQB is 90 degrees. So what we need is we need a separate argument to go back the other, in order to show that the locus is the circle and not that the circle is a subset of the locus. We need another argument which has the implication going the other way. So Nagvi's argument tells me that if P lies on a semicircle or lies on a circle with diameter AB, that implies that the angle APB is equal to 90 degrees. What we need to do now is to try and get an argument that goes the other way, that tells me that if APB is equal to 90 degrees, then that implies that P lies on the semicircle with diameter AB. In order to show that the locus is the circle, we would need to show both of these conditions. If we'd only shown this condition, then we would only have shown that the point has to lie on the circle, but we wouldn't have shown that every point on the circle works. Okay, so how do we prove the argument in the other direction? Okay, so there's lots and lots of different proofs, but I'm going to give one which is which has got a nice which is a nice trick that physicists use a lot, because I know a lot of you are budding physicists. So what I'm going to do is I'm going to let P be any point such that APB is equal to 90 degrees. Now I'm going to do this using coordinate geometry. And this is a trick, as I say, a trick that you'll meet time and time again in physics. So at the moment, I just know that the points A, P, and B are related by this diagram, that APB is 90 degrees. What I'm going to do is I'm going to introduce a set of coordinate axes. So I'm going to do it by coordinate geometry. And I'm going to do this trick that, as I say, the physicists love, is I'm going to choose the axes as much to my advantage as is possible. Okay, and so what I'm going to do is I'm going to put P at the origin, because I can always just rotate my sheet of paper such that P is at the origin. And these two perpendicular lines, whoops, I'm going to turn off ink to shape. These two perpendicular lines, I'm going to make the X and the Y axis. So I can always choose the axes so that they are like this, so that A has got coordinate x0 because it's somewhere on the x-axis. B is 0y because it's somewhere on the y-axis. And O is the origin. And now I'm going to draw the line AB. In order to show that O lies on a semicircle, what geometric fact would I need to prove based on this diagram? So what I need to show is that O lies on a semicircle with diameter AB, which means that O lies on a circle whose center is the midpoint of AB. So if I mark the midpoint of AB, if I mark it M, I need to show, if I can show that OM is equal to MB, which, because M is the midpoint, is equal to MA, then O will lie on a circle with center M. So I will show, so if M is the midpoint of AB, it's sufficient to prove that OM is equal to half AB. So the length OM is half of the length of AB. Right, so let's do this. And now it's going to be quite simple. So the if A and B are as given, x0 and 0y. The coordinates of M are x over 2, y over 2. And so the length OM by Pythagoras is, I can get it from its coordinates. So its x coordinate is x over 2. Its y coordinate is y over 2. So by Pythagoras, OM is just the square root of x squared over x over 2 all squared plus y over 2 all squared, which is the square root of x squared plus y squared over 4, which is 1/2 square root of x squared plus y squared. But that square root of x squared plus y squared is just what Pythagoras' theorem would give me as the length of AB. Okay, so what that shows is that the three lengths that I've marked, OM, MB, and MA, are all equal to one another, so they all lie on a circle with centre M. A slightly neater geometric argument would just be that if I had drawn the diagram as before, I could just add a new point C to sort of complete the rectangle. And then if I draw the other diagonal, it's geometrically obvious, it's just a little bit of congruent triangle chasing, that the two diagonals of a right angle by symmetry just cross and just bisect one another. So all four of those lengths are equal. And if all four of those lengths are equal, that means that they all lie on a circle with center M. So they all lie on a circle with diameter AB. So what we now have is two separate arguments. We've got one argument, which was Nag's, that tells me that if P lies on a circle, that implies the angle APB is 90 degrees. And then I've got the second argument, which tells me that if APB is equal to 90 degrees, then P lies on a circle. And to show that the locus is the circle, all of the circle, and nothing but the circle, you need both parts of those arguments. Okay. I'm just going to see if there's any questions on the chat. If anyone's got any questions about this example, then put them in the chat now. Otherwise, just put a thumbs up and we will move on. Zena, you said doesn't having M as x over 2, comma y over 2 require that OAB equals 40 degrees? No, that would, having it as 45 degrees would imply that would be the assumption there. The thing which would follow if it was 45 degrees was the x and y coordinate would be the same. Okay, but even if it's not 40 degrees, yeah, if this, let's say A was at the point 2, 0, and B was at the point 0, 10, where would the midpoint of those two of that line be? Well, if you shine a light downwards and you consider the shadow cast by the midpoint, then the shadow cast by the midpoint would be directly under the midpoint, which would be halfway along between 0 and 2. So the x coordinate of the midpoint would be 1. If you consider shining a horizontal light and thinking where the midpoint casts a shadow on the y-axis, again, that would be halfway up. So that would be at a height 5. So the coordinates would be 1, 5. So the coordinates of the midpoint would always just be half of the x coordinate and half of the y coordinate. Okay. Does anyone have any questions about this example, or are people happy to move on? No. I'm glad someone put no makes sense, and I initially saw the no, which made me think that they weren't happy to move on, but now I'm relieved that they are happy to move on. If you want extension to this problem, I'm just going to tweak it slightly. Okay, and I'm now going to give you a new locus. I'm going to say let A and B be fixed points. And now what I'm going to tell you is that the set of points P satisfy the angle APB equals 20 degrees. Okay, so here's A, here's B. And P is any point where the angle APB is 20 degrees. And the question here is, what would the locus be? Okay, and again, there would be two parts to finding the locus. One, finding a set of points such that every point on that set satisfied this condition, and then showing that every point that satisfied this condition lies on that set. Okay, right, let's move on to the sheet itself. I'm just inserting that into my OneNote. Ah, yeah. So the first example that it gives me is I'll go through the example, okay, because it's such a fundamental one, and it's something which you've probably done at school. But I introduce it with a little story, okay. So I imagine two warring kings, okay. So my warring kings, I've got King A, King Alberic, and he's got a castle at point A. And then I've got King B, who's got a castle at King Balthazar has got a castle at point B. And they divide the kingdom in such a way that if a point is closer to B than to A, like this one, it belongs to Balthazar. If it's closer to A than to B, like this one, it belongs to Alberic. Obviously, there's going to be some boundary wall between their kingdom. And so that boundary wall will be the set of points where the distance from A to B is the same. Okay, and this is either a test of seeing whether you've made a start on the sheet or whether you've got good geometric intuition. Can anyone tell me what that blue, well, I'm going to say line, could be a curve, but what that blue wall will be? Okay, so Lucas suggested that it's the perpendicular bisector of AB. Okay. And so let's see if he's right. So first of all, let's take the points AB and let's draw the perpendicular bisector. So the perpendicular bisector is the line which passes through M, which is the midpoint of AB, and which is perpendicular to AB. if I now take P as any point on the perpendicular bisector, let's consider the length of AP and the length of BP. Well, by Pythagoras, AP squared is clearly AM squared plus MP squared. Okay. But now, because M is the midpoint, AM squared is numerically equal to MB squared. So this is equal to MB squared plus MP squared. Okay, but now if we look at this expression, MB squared is this length over here on the right. MP squared is still the line going up. So again, Pythagoras gives me that this is equal to BP squared. So what this shows, well, actually, no, let me turn this to you. So this little argument here, so this bit of geometry, can anybody tell me what this piece of what this argument here has shown logically? Has it shown that the desired locus is definitely the perpendicular bisector? Or has it only shown part of it? And if it has shown part of it, what has it shown? So yes, the two. We've got another vote for saying that this argument has shown it fully. Okay. So I'm going to really labor this point of logic. What this argument has shown is that if I take a point on the perpendicular bisector, so if P is a point on the perpendicular bisector, then this argument shows that the distance AP is equal to BP. So in other words, and that means that the point P is on the wall. So this shows that if P is on the perpendicular bisector, then P is on the wall between the kingdoms. So what it shows is that the wall between the kingdoms contains the perpendicular bisector. Okay. So what that means is that the wall between any point that's on the perpendicular bisector is on the wall. But what it's not ruled out yet is that there could be points that aren't on the perpendicular bisector, but that nevertheless are on the wall. Okay, the implication has only been that if I start with a point on the perpendicular bisector, then I do this piece of geometry and I show that the two distances are the same. What it hasn't guaranteed is that if the two distances are the same, then I am on the perpendicular bisector. And so there's a subtly different piece of geometry or geometric argument that I'm going to use to show that. And I really would recommend all of you just to zoom in and try and see why these two arguments are different. So what I'm going to do is I'm going to do I'm going to do this argument. I'm going to say, let P be on the wall. Okay. So in other words, AP is equal to PB. So I've got my points A and B, and now I've got the point P. And all I'm going to assume is that these two distances, AP and PB, are the same. Okay. Now what I'm going to do is I'm going to look at I'm going to assume that I can find this. I'm going to find this point N on the line AB such that ANP is a right angle. So this line here, MP, is perpendicular to AB. Okay. Now, where do you think that point N is going to be? Yeah, so we think it's going to be the midpoint of, we think that it's going to be the midpoint of AB. If we can show that it is the midpoint of AB, then P is exactly lying on the perpendicular bisector. So what I'm going to do now is I'm going to say that AN, so this distance AN, which is this distance along the bottom, so AN squared. By Pythagoras, that is AP squared minus NP squared. But now I can use my the fact that I've got isosceles triangles. And I'm going to use the fact that AP is equal to PB. So now I can say that AN squared is PB squared minus NP squared. But now PB squared, so PB is just this diagonal over here. NP is still the line going up. So PB squared and NP squared are again lengths of a right angle triangle, but this time the lengths in the right angle triangle NBP. So what I can say is that this PB squared minus NP squared is BN squared. So therefore AN equals BN. So therefore N is the midpoint of AB. Okay, and so now, and because the angle ANP is equal to 90 degrees, P lies on the perpendicular bisector. So the argument on the left shows that on its own shows that every point on the perpendicular bisector is on the wall, but doesn't rule out there being points on the wall that aren't on the perpendicular bisector. The argument on the right shows that if a point is on the wall, then it is on the perpendicular bisector. But the argument on the right on its own does not show that there's not gaps, that there's not gaps in the wall. So the argument on the right only shows that the wall is potentially like this, is a subset of points on the perpendicular bisector, but doesn't prove that every point on the perpendicular bisector is on the wall. If you put the two arguments together, then you're done, because then you've shown that every point on the wall is on the perpendicular bisector, and conversely, every point on the perpendicular bisector is on the wall. And so what we can then say is that the perpendicular bisector is exactly the locus of the points that are equidistant from each point. Okay. Does anyone have any questions about that? Good, all makes sense. What the sheet also explains is that this example not only gives a fact about the perpendicular bisector in terms of it being on a locus, but it also gives a practical recipe for how to draw a perpendicular bisector. Okay, and I'm just going to change the program that I'm in. I'm going to go to I'm just going to change my share. Where's my control? So what that last example does is shows me that if I take 2 points A and B, that the set of points that are equidistant from them lie on the perpendicular bisector, and conversely, the perpendicular bisector is the set of points which are equidistant from them. So if I draw circles with center A and B that have got the same radius, so I'm just going to So what I've drawn here is a circle whose center is A and goes through B. If I now draw a circle whose center is B and goes through A, these two circles have got the same radius. If I now get the points where these two circles intersect, C and D, then from what I've just shown, C and D lie on the perpendicular bisector. But the perpendicular bisector is a straight line, and a straight line is uniquely determined by any 2 points. So if I join those 2 points up with a straight line, this line that I've just drawn is the perpendicular bisector. Okay. And what that is in the context of the sheet is a practical recipe for drawing a perpendicular bisector. Okay, if we just want to convince ourselves, if I measure this angle AEC, then look, it's exactly 90 degrees. Okay, what if I measure the length from A to E? That's got length 5. If I measure the length from B to E, then it's got the same length. So that line that I've just drawn is the perpendicular bisector. What that is a geometric construction. Okay, and geometric constructions were very important historically, initially with the ancient Greeks, but I think the civilization that's most closely associated with them is the Arabic mathematicians, the Muslim mathematicians. If any of you have had the pleasure to visit the Islamic world or visit places which were formerly in the Islamic world, like southern Spain, you might have seen some of the really elaborate tiling patterns from some. So a very famous example, this is in southern Spain, in Seville. Why is my internet being so slow? the Islamic mathematicians made lots and lots of really beautiful and really intricate tiling patterns involving 6-pointed stars, 8-pointed stars, 12-pointed stars, tessellating hexagons, squares, and so forth. And all of those, they would learn at the madrasas how to do the constructions using rulers and using ruler and compass. What I'll share with you next is a really lovely app. My daughter, who's 7, has already started to play around with this. This is an app called Euclidia.xyz. And if I just sign in, this is a little game that challenges you to construct things using a ruler and compass. And some of the questions from the sheet are similar to this, some are not. So let's have a look at the first example. So, and I really, part of me sort of recommends that you do ruler and compass constructions with a ruler and compass. But I think maybe you'll get more bang for your buck playing around on the computer. So here's an example. This is an example of the Euclidia game. Any one of these questions could be a good example for the problem sheet. So this is the first one where it says construct an equilateral triangle. So the shape in the top left-hand corner is the target shape. So can anyone, does anyone want to suggest how I can construct an equilateral triangle having been given this straight line? Anyone feel brave and want to unmute themselves and talk me through what to do? Okay, yeah, so Lucas said, same as the perpendicular bisector, but then join up to C. Okay, so if I just repeat what I did with the perpendicular bisector, so drawing a circle going in each ways, then either of the points where the circles intersect are equidistant from the points A and B, and the distance are the same. So if I just join these up, I then have a equilateral triangle. If you play this game, and I recommend it, it gets really, really addictive. At this stage, it will then tell you whether you've completed it and also whether you've done it in the fewest number of elementary operations. Okay, so I did that with drawing 4 things in total, 2 lines and 2 circles, which is 4 elementary operations, and that is the best possible. Okay. If you work your way through Euclidia, it then says construct an angle with 60 degrees if you've got a given side. And as you can probably realize, that's just very similar to drawing an equilateral triangle. We just need to pick a point on that line and then just do what we did before to get the equilateral triangle. And that constructs an angle of 60 degrees. As you progress further through this game, it gives you more and more tools. Okay, so for example, once you've actually got once you've got the perpendicular bisector construction, so this should be very familiar now. So once you complete the level that gives you a perpendicular bisector, it then realizes that you don't want to just have to go through that motion every time you want a perpendicular bisector. What it then gives you is a tool that allows you to just draw a perpendicular bisector if you're given 2 points. So the perpendicular bisector tool just draws the perpendicular bisector with 2 points. I love this game. So the next challenge is it gives you 2 points and it wants you to find the midpoint. Well, what you probably realize is that if you draw the perpendicular bisector, then the midpoint is the point in the middle. An interesting thing, we'll just do one more. So this says, inscribe a circle in a square. So the thing that you're given is the square. What they then ask you to do is draw a circle that lies inside of that square. So any suggestions of using the tools that we've done, how to construct that circle lying inside of a square?
Can I say something?
Yeah.
So you could draw 2 lines from corner to corner, then just draw a circle from the intersection.
Right, so if I draw 2 lines from circle to circle, that gives me the midpoint of a square. Okay. What I could for sure do then is draw a circle that contained the square. So for example, I could just go out to any one of the corners and I've got my square inside a circle. How am I going to get my circle inside a square? So what? Obviously, I could just do it like...
You could,
Sorry, carry on.
You could make a perpendicular bisect between the squares where they intersect again through the same point.
Excellent. So if I do a perpendicular bisector between these 2 corners, that perpendicular bisector will also go through the midpoint of the square, because that point in the center of the square is just like the center of the square. And what's the advantage of doing that is it also gives me the midpoint of the top edge. And now what would I do, Mark?
Now you could just draw a circle with radius at the center and with center at the center of the square, and a radius with its edge at the midpoint of the square.
Excellent. So I could just go to the top. I could just go from the center of the square to the midpoint here, and then that circle lies exactly inside it. Now notice that we've done more. We ended up doing more work than we needed to, because we maybe drew more lines than were strictly necessary. I have to confess, I get very, very pedantic, well, not pedantic, but like on the higher levels of this game, I get very frustrated if I complete a level, but then I realize that I haven't done it in the most efficient way possible, and it can get very hard sometimes to find the most efficient ways. This question, the rhombus in the rectangle, is on the sheet, so I won't spoil that here. Hopefully, you'll be inspired to go away and play Euclidia XYZ. Does anyone have any questions about those early constructions, the principle of constructions, or are people happy to move on? If you're happy to move on, just put a smiley face, put a thumbs up in the chat. Right, happy to move on. Excellent. Right, I'm going to go back to ordinary GeoGebra here. And I'm going to do some relatively famous bits of geometry. So I'm going to start off by drawing a triangle. And what I'm going to do is I'm going to draw a perpendicular bisector of the side AB. That's perilously close to C, okay? It doesn't need to be, it's just because of how I drew the circle. I'm going to draw a second perpendicular bisector of AC. And now I'm going to draw a third perpendicular bisector of BC. And I'm going to notice something interesting. Does anybody want to guess what I'm going to notice? So Luke has suggested that they're all going to intersect at the same point. Okay, so let's do my third perpendicular bisector. And it looks like they've intersected at the same point. And if I do my intersection tool, there's a single point there. But, okay, that might have just been chance. Okay, but let's see. I'm going to move point C around. And they always seem to intersect at a single point D. Does that, I'm going to take a vote now. Does that point D always lie inside the triangle? If you think yes, vote yes. If you think no, vote no. And if you really want, if you think no, that it doesn't always lie inside the triangle, can you try and give me a condition of when it will lie inside the triangle and when it won't? So initially it always seems to lie inside of the triangle, but sometimes it lies outside of the triangle. That's interesting. Okay, so I'll leave that as a little teaser for the moment. But what we're going to return to is the question of why do those three lines always meet at a point? So why do the three perpendicular bisectors always meet at a point? So in order to do that, I'm going to need to stop this share and go back to my OneNote. And in my OneNote, I'm going to make this claim that if ABC is any triangle, then the three perpendicular bisectors meet at a point. Okay, so let's give a proof. So if I draw the first perpendicular bisector, that's just a line. If I draw a second perpendicular bisector, that's another line. And why will those two lines for sure intersect? Well, two lines intersect as long as they're not parallel. Now, these two perpendicular bisectors would only be parallel if the two lines themselves were parallel. But two edges of a triangle can't be parallel because then they wouldn't be different sides of a triangle. If the two sides of a triangle were parallel, they would just be one side. So that's the two perpendicular. So any two perpendicular bisectors are going to meet at a point. What we want to do now is try to understand why the third perpendicular bisector is guaranteed to go through that same point. So who can remind me what categorizes a perpendicular bisector? So what can you tell me about every point on this blue line? Oh, answers in the chat. Yeah, so that blue line is equidistant from AB. Okay, so that point G is the same distance from A as it is from B. Similar question. What property of points is satisfied by the points on the green line? Or on the line that I've the green line, the one which I've just highlighted blue. It's equidistant from A and C. So that means that AG is equal to GC. But now AG is equal to AB because it's on the perpendicular bisector from AB. But AG is equal to GC. So now we can conclude that GC is equal to GB. In other words, these two lengths, this one and this one, are the same. So what does that tell me about G? Well, that tells me that it's equidistant from B and C. And if it's equidistant from B and C, it must lie on the third perpendicular bisector. So if I just go back to my construction in GeoGebra, that this point D, where the three perpendicular bisectors meet, if I was to draw a circle with D, then it would pass through the 3 points on the triangle. Now, I need to unfortunately just dash to the loo very, very quickly. While I dash to the loo, that's a good little thinking break. What I would like you to do is now, with this in mind, see if you can answer the question that I posed earlier about when this point D, where the three perpendicular bisectors meet, the circumcenter, when it lies outside of the triangle and when it lies inside of the triangle. I will be 2 minutes. Okay, I'm back. So, does anybody want to give a suggestion for when this special point D has got a name, it's called the circumcenter. Does anyone want to suggest when the circumcenter is inside the triangle and when it's outside of the triangle? Okay, so the claim is, and there's a correct answer in the chat, that it's when ACB is obtuse. And I will leave this as an exercise to the read, to prove this, but I can at least point to this being the case. So let's try and get the edge case. Okay, so let's try and get the edge case when D lies on, so when the circumcenter lies on the line AB. Okay, now when have we met this edge case exactly? Oh, we've met this edge case because we know that when a point lies, so if we know that if the point D lies on AB, then it must be the midpoint of AB because it's equidistant from AB. So AB must be the diameter. Ah, it's almost like it was planned. Okay, so this was the very start of the lesson. At the very start of the lesson, we know that if AB is the diameter of a circle, then ACB is 90 degrees. So if we have a right angle triangle, then D lies on AB. So 90 degrees is the edge case. Okay, and I'll leave it as an exercise to prove it, but it seems obvious that one side of the edge case is going to be when ACB is obtuse. This looks like an obtuse angle, and it looks like D is outside of the triangle. The other side of the edge case is going to be when ACB is acute, and that's here. This looks like an acute angle, and here that D lies inside of the circle. Right, we're just going to do a little bit of I don't know, going to do a little bit of fun geometry now. You might be thinking, like a lot of people think, that this seems somewhat zen compared to like normal maths. Like, okay, this is quite nice that there's a construction of a certain circle, that I can draw a circle that goes around the points of a triangle. But it seems a bit disconnected from like real maths and useful maths. But I'm going to use this result to prove a nice bit of maths. What I'm going to do is I'm going to ask the question, what is the radius of this circumcircle? So what is the radius? If I've got a triangle ABC, what is the radius of the circumcircle? Okay, this isn't, well, there could be questions like this on the sheet. There is a question like this on the sheet towards the end, but let's have a look at this. So I'm going to do a new share, and so my question is now going to be, I know that the I know that the 3 points on a triangle can always be contained within a circle. I'm now going to try and find what the radius of this circumcircle is. So let's label one of the angles here in standard notation. So this angle at C, we would normally label as C. Okay, using our circle theorems, which I think you've probably done at school. Can anyone tell me what this angle here, the other side of the center, is going to be? Yeah, well done. Luke said that's 2C. Okay. If you've not done circle theorems at school, I would recommend doing a little bit of, you can do a lot of isosceles triangles. Yeah, so you could call this angle here X. This angle here also would be X. So this angle here would be 180 minus 2x. And so if I carry this straight line on here, this angle would be 2x. By very similar geometry, if this angle here was y, looking at this isosceles triangle tells me that this angle is also y, which tells me that this angle is 180 minus 2y, which then tells me that this angle is 2y. So the green and the red angle together is 2x plus 2y, but that's just double this x plus y up here. Okay, but that's a standard circle theorem. So Luke has told me that if this angle is C, this angle here is 2 times C. Well, let's look at the triangle at the bottom. So the triangle at the bottom, so this is my triangle ADB. AD is R, DB is R. So how can I cut this? So this is what type of triangle? Well, this is clearly a isosceles triangle. What we also know is we know that D, because it's equidistant from A and B, lies on the perpendicular bisector. Okay. In fact, this line here was just the perpendicular bisector. Now, the distance from A to M is half of the distance from A to B. And so in standard notation, that distance A to M is side length C over 2. What's this angle ADM equal to? Well, that angle ADM is just cutting the angle 2C in half. Okay. Now, if the whole angle is 2C, angle ADM is going to equal C. But now we can just do a little bit of trigonometry on this right angle triangle. So on that right angle triangle, we have that sine of C is the opposite, which is C over 2, divided by the hypotenuse, which is R. And if I just rearrange this a little bit, I get that 2R, which is the diameter, is equal to C divided by sine C. Okay, now question for you all. Without doing any extra work whatsoever, can you tell me something else that C over sine C is equal to? And this is an important concept. Now, I could do a whole load of new geometry, but there's a very important idea. Okay. In order to get that 2R is C over sine C, it just relied on the fact that I label the angle at the point C, capital C, and I label the side length of the side opposite capital C as little c. But now I'm going to do a little sleight of hand, right? I'm not going to call it capital C anymore. I'm going to call this point B. Okay, which tells me that 2R is equal to B over sine B over, is equal to B over sine B. Okay. But it would seem bizarre. What I could also do is I could have just rotated the triangle so B was at C and then called BC. It can't, this radius must be the same, okay, however I label up the triangle, okay? And it can't depend on the fact that I've labeled this point C in order for it to be C over sine C. Okay, there's no, if the radius, if the diameter was not B over sine B, but was B over cos B, for example, that would mean that the point that we've called C and the point that we've called B would behave differently. But why should they behave differently? They're just 2 points on the triangle. Or if it was B over sine B times 2, they would behave differently. Okay, so this really important concept is that the formula that we get for the diameter just depends on the triangle. The formula that we've got here just involves the point C, but by symmetry, there's nothing special about the point C. So the formula that we would get if we use the point B must be the same formula. And the single word that explains that idea is symmetry. So by symmetry, we can say that 2R is equal to C over sine C is equal to B over sine B is equal to A over sine A. Okay, and just as an aside, you probably know this result from school because this result is taught often, is that it's the sine rule. But this extra little bit of geometry has sort of fallen off the GCSE syllabus a little bit. It's fallen off the GCSE syllabus to actually tell you what A over sine A is. And it turns out that A over sine A is the diameter of the circumcircle. Okay, any questions about that example? So this example takes a construction. So in this case, a construction of a circumcircle, and then it uses that construction to prove a fact about a triangle, in this case, the sine rule. Okay, if anyone's got any questions about this example, put that into the chat. If not, can you just indicate in the chat that you're happy to move on? Okay, so we've got a happy to move on. Oh, we've also got a comment that said that it's really nice, to see the sine rule proved. Yeah, I think it's really nice to see the sine rule proved as well. I think it's also particularly nice to know that it's not that these quantities are not just equal, but they are equal to something. Okay, well, my word, we're running a little bit short of time. The second construction that is on my sheet and the second construction that is on GCSE is the construction of an angle bisector. And the idea of the angle bisector construction relies on something that we've already seen, which is that if we've got an isosceles triangle, so if we've got a triangle which is isosceles, then to the angle bisector of an isosceles triangle, we'll chop it into two congruent halves. Okay, because I think that's obvious, because if these two angles are the same, then the two enclosed lengths of the angles are the same. But if you've just got two enclosed lengths and an angle, the third side is forced. So the angle bisector chops a isosceles triangle into two congruent halves. Does anybody want to suggest how else I can chop an isosceles triangle into two congruent halves? So if I've got an isosceles triangle, ABC, what line can I draw that will chop it into two congruent halves? The perpendicular bisector. Excellent. And this proof here at the very top, someone even mentioned congruent triangles here, but this proof here where I prove the perpendicular bisector is the point which is the set of points which is equidistant, is exactly an argument about isosceles triangles. So I know that if I draw an isosceles triangle, that the perpendicular bisector is also the angle bisector. And so if I just get a new share, if I just go back to GeoGebra, so if I just start again, this will give me the, there must be a way of getting, how do I get a new? Okay, so if I'm given an angle, any old angle, I can start off by creating an isosceles triangle just by drawing any circle. Okay, because if I just draw any circle, where that circle meets my enclosed angle, so those points E and F, this triangle EBF is going to be an isosceles triangle. But if I now just get the perpendicular bisector of E and F, that will also be the angle bisector. Okay, and if you just want to convince yourself of that, if I get this point, let's see. Let's measure the angles. Okay, so that's for oops. Okay. That's those two angles are the same. Right, let's have a let's finish with another nice piece of geometry. So what I'm going to do is I'm going to do something similar to before, is I'm going to draw a triangle. So here's my triangle. And what I'm going to do is I'm going to draw the angle bisectors of the three angles. So I'm going to draw the angle bisector of ABC. Then I'm going to draw the angle bisector of BCA. And they meet in a point. Does anybody want to make a guess, an intelligent guess of what they think might happen when I draw the third angle bisector? It's all going to meet in the same point, is the claim. Okay, so let's see. So I'm going to draw my third angle bisector. So this is BAD. And it really does seem to lie in the same point. Okay. I do recommend playing around with GeoGebra. GeoGebra is really, really useful if you do something like sort of BMO geometry. You know, you can, you know, obviously you should try and solve the problems, but if you get stuck on the problems, a good thing to do is try and draw them in GeoGebra and then see if there's any properties that are stable no matter how you draw the diagram. Okay, it turns out, and it's proved on the sheet, that those three angle bisectors do all meet in a point. And I will show you a nice property that that point has, which you may or may not have seen. But the angle bisector is and it's introduced like this on the sheet, could be considered as the wall between the kingdom based on the sides of the triangle, because the points on this angle bisector BE are equidistant from sides AB and BD. By a similar line of reasoning, that point E is equidistant from all three of the sides. So the circumcenter was equidistant from all three of the vertices, whereas this point is equidistant from all three of the sides. Okay, so let's see what that what property that gives us. So what I'm going to do is I'm just going to drop a perpendicular from E to one of the sides. So I'm just going to draw a circle with center E. I'm going to let it meet the bottom edge at 2 points F and G. By a little bit of geometry, the point, because F and G are equidistant from E, E lies on the perpendicular bisector of G and F. So if I draw the perpendicular bisector of G and F, that passes through E. So in other words, this point down here, H, is just directly below E on the bottom edge. So this point E, this line EH is the shortest distance from E to the edge AB. But what we decided earlier was that this point E was equidistant from all three of the edges. So if I draw a circle with center E that goes through H, by the power of mathematics, and I'll just hide all the other circles. Oops. I'll just make this a little bit less cluttered. So what I've done is I've got the oops. I've got the point E, which is where the angle bisectors all meet. I've then got the point H, which is the closest distance of that point to the line BC. And that circle centered on E touches the line BC, but then also touches all three of those of the sides. And so what I can see is, and this remains stable even as I move D around. And so this shows me that wherever I draw wherever I move the point D to, the angle bisectors all meet at a common point, and that common point is the center of a circle that just touches the inside of a triangle, and that's called the incircle. And if you work on the sheet, there's some nice bits of geometry based around the incircle. There's also other circles that you can draw called the X circle, and if the sheet isn't edited, the high point of the sheet is that it will prove a lovely little bit of mathematics called Heron's formula, which gives you the area of a triangle in terms of its side lengths. Okay, I think that puts us out of time, if not a little bit over time. So I will finish there, unless anybody has got any questions. Okay. Oh, I've got someone saying thank you. That was interesting. Okay. So yeah, recap of what we've done. We've shown that the locus of a point where APB is 90 degrees is a circle. We've shown the locus of points which are equidistant from 2 points is a perpendicular bisector. We've shown that the perpendicular bisector of the three sides of a triangle meet at a common point, which is the circumcenter. So you can always draw a circle that contains the 3 points of a triangle. We use that to prove the sine rule. And then we also use the perpendicular bisector to draw an angle bisector and show that the angle bisectors of a triangle also all meet at a point. And that is the incenter of a triangle. So in a short amount of time, we have done a lot of classical geometry. And I hope you enjoyed it. So thank you very much for this evening. Enjoy the rest of your day.